Thank you. I'll try to be quick. And what I am going to talk about is what we can do beyond AVO, the conventional AVO we all are aware of. And I want to take you a step beyond AVO and see what we can do and end up with a real data example. So if I know how to forward, read this one. So I am just briefly go over. We all know about what AVO is, amplitude variation with offsets. Then I'm going to move into the assumptions we make when we do our AVO-based analysis, AVO-based inversion. Then I'm going to introduce the step beyond AVO, which we call full waveform inversion, where we not only look at the primary reflections, but we include the multiples and more converted. So we look at the full waveform. Then I'm going to show a real data example, go over the road ahead, and we'll talk about some of the deliverables we can provide in terms of this as I go along. So what is AVO and AVO inversion, what we do today? Those are all based on reflection coefficient. We sometimes use exact formula, we can sometimes use linearized formula, and we all know, I'm going to use only one equation and we'll go over quickly. We all know this is the linearized form of AVO inversion. It says that P wave reflection coefficient is a function of the angle of incidence with some coefficients, and those coefficients A, B, and C are lithological properties. So what we basically essentially do, somehow on my seismic data, we convert those offsets we collect to angles, and then I can say go along one line here and pick the amplitudes. So those are the amplitudes, and I can say this is the amplitude at a small angle, say theta 1, theta 2, and we can call them those, we can call them those amplitudes, we can pick the amplitudes for example, and we can call them D1, D2, D3, D4. Those are the P wave reflection coefficients. So D1 belongs to the smallest angle, and Dn should be the largest angle, and they are somehow related to these A, B, and C parameters, and we can immediately see that we can write a matrix equation like this. So this is basically, what we are basically doing in AVO, we cast this like a D equal to Gn type of procedure, where D is my data, and N is the model, which is ABC, and G in this case is a matrix. And when it is a matrix, this is a classical problem, and we can formulate as a least square inversion, and we can get the estimated model directly from the data. Actually, this should be small d, and G. And sometimes what we do is, we know this could be unstable. We can add a small diagonal element to this so that this inversion becomes stable, and that becomes a damped d-square. So this is essentially what the AVO inversion is all about. Now let's go forward. So what we can do in AVO, we can do this. This is a very fast process. So every C and P, we can compute A, B, and C, compute different lithological and reservoir fluid attributes, interpret results. And what is the problem? Why do you want to go a step beyond? So in order to do that, let me just clarify a few of the things. What are the issues in AVO inversion? So I'm going to talk about two issues. First is AVO and AVA provides the narrow band model. So if you look at the AVO, we have already NMO corrected the gathers. So what we get is a contrast. This A, B, and C are contrasting P wave velocities, contrasting with shear wave velocities, and contrasting densities. That's what they are related to. So essentially, what is typically done, an AVO inversion will give you a high frequency model, and we have to get the low frequency model from somewhere, and then we add the two to get the broadband model. That's exactly what we do when we do our AVO-based inversion. And then the next issue is more fundamental in nature, and that is, it assumes, when we are doing AVO, it assumes my pre-stack reflection amplitudes are proportional to plane P-wave P2P reflection coefficients. That means it does not have any other, this is equivalent to assuming a convolutional type of modeling. So it does not have anything but P-wave primary reflections. Means we do not have mode converted events, we do not have any multiple scattering, we do not have any transmission loss. Let me clarify this deviant modeling example. So what I am going to do here in the next, the way to handle all these wave propagation effects is to use a methodology that can handle this interference. This is exactly what we need to do. So that actually requires a rigorous solution of the elastic wave equation. And that is what the pre-stack full waveform inversion is all about. We are talking about, and that is what we are calling is the step beyond our conventional AVO and AVA-based methods. So we talked about this. This is our D equal to GA problem, where we said that we can formulate that as a least square or a damped least square solution. But now, when it was AVO, that G was nothing but a matrix. We had a data vector here, we have a model vector here, and data and model are related by a matrix. But in wave equation, this is not a matrix, it's a wave equation operation. So we have to solve the rigorous wave equation. We have to rigorously solve the wave equation. So this operator G is not a simple matrix multiplication. That is what makes the situation more complex. So I'm not going to talk about how we solve the waveform inversion, but what I am going to do is I'm going to go and give an example. But before I give an example, I'm just going to give an example, and that example is going to be on a real seismic data, a single location, and this is actually a global optimization method. When it comes to inversion, waveform inversion, there is a linearized version and there is a global version, but we chose to take the global optimization because we wanted to handle the non-uniqueness of the problem. So I am going to go over the global optimization, and if you are interested in knowing how to deal with the global optimization and local, I can explain to you later on, but due to the limitation of time, I am just going to switch over and give an example. So there was a well, but what I did is, in this inversion, I only used the well to fit one relationship between VP and VS and one relationship between VP and density, that's it. So we started with a VP, which is basically, I just flattened the gathers. And that flattening, the velocity analysis to flatten the gathers, that was my VP to start with. Then I took the log, I fitted one curve between VP and VS, and that is my VS, and fitted one curve between VP and density, and that was my density. So this is my gather on the right hand side, on the far right. This is the P wave velocity that was used. So it was manually flattened using this P wave velocity, and then use the density VP VS relationship to get an estimate of VS. This is my VS estimate, and then use the VP density relation, and this is my density. So it took this as my initial model and got into this global inversion where essentially it keeps on. So what it does, it basically starts with an initial model and provides a search window between I provide a search window of VP. So there is a minimum window and a maximum window, a search window of VS and search window of density, and it randomly generates a lot of models, computes theoretical seismograms, and matches with the observed seismogram, and keeps changing till it finds an optimum match. That's exactly what it does. So this is the result. This is the final result of the inversion right here, and you can see this initial starting model is the one in blue or whatever the color is. The red one is the inverted model, and the black one is the well. And of course it is not perfect. There are some issues, but it is, I think, doing a pretty good job. It is trying to say, it started